All right. So when we left off, we were talking about how to use this chart to predict whether a solid product would form or whether it would not. So whether it is soluble or insoluble product from a double replacement reaction, a precipitation reaction. So for things like mercury chloride and sodium carbonate, we determined their solubility. So for the chlorines are soluble, but if it's with mercury, it is insoluble. So that's how we're using this chart. Carbonates are insoluble, but unless it's with an alkali metal. Sodium is an alkali metal, so therefore sodium carbonate is soluble. It would dissolve. That's why we say it's aqueous. It is aqueous. It would dissolve, whereas mercury chloride would be a solid product. It would not dissolve in water. Okay. All right, so let's further investigate this then. So here we see that the way that we would set this up, you'd have the two reactants, lead nitrate plus sodium chloride. So essentially the way that this would work is you have two tubes, right? You have these two tubes. And one of them has the lead 2 plus in it, and the other one has the NO3 with the NO3 minus. The other one has the sodium plus and the Cl minus. And then you take one tube and you put it into the other one so that you mix all those ions together. And when you mix them all together into one tube, okay, the lead and the nitrate find each other and they form a solid product, okay? Not the lead and the nitrate, that's what we started with. The lead and the chlorine. The lead and the chlorine find each other and they form a solid product, and the sodium and the nitrates just remain dissolved. They remain in solution, dissolved. Okay? So then we get a solid product coming out of solution as our precipitate. That's a solid. The sodium and the nitrate remain aqueous. So they actually didn't do anything. Okay? So this is a double replacement reaction because the lead and the sodium are switching places. They're just switching partners. So it's a double replacement. Okay? They're switching partners. So let's predict whether precipitates will form from these reactions right here. Okay? We have potassium, we have chlorine, we have silver, and we have nitrate. We have potassium, we have acetate, we have silver, and we have nitrate. Okay? All right. So, in these reactions, we need to figure out the charges. Potassium has a positive 1 charge, right? Chlorine has a negative 1 charge. Silver has a plus 1 charge. So everything in the first one just has positive or negative 1 charges. In the bottom one, we have potassium plus. Silver is also plus. So everything also has a negative 1 or positive 1 charge. I made it easy. Okay? So now we just have to figure out the formulas. So we have KCl, 1:1, plus silver nitrate, 1 silver, 1 nitrate. Okay? These are going to be double replacement reactions. So what are my products? Silver chloride, potassium nitrate. Now, from what we've learned about the metals found in the first column of the periodic table, the very first column, what do we know about them? Could they ever be a precipitate? Could potassium ever form a precipitate? Can't. Okay? Because it's in the very first column. It's a metal in the very first column. And those metals, they're always soluble. No matter what, they're always soluble. So this potassium nitrate will be aqueous. So the only question that really remains is, does silver chloride form a precipitate or not? So how are we going to answer that question? Look at this chart. How are we going to determine if silver chloride is solid or if it's aqueous? It's insoluble. Why? Chlorines are soluble. But silver is an exception to the solubility of silver, or of chlorines, I'm sorry. So silver chloride is insoluble. So these are soluble things over here. Over here, they are insoluble. Okay? These are insoluble, but over here they are soluble because they are the exceptions to those. Okay? So that's how we're reading this chart. So this would be a solid product. So here I would write silver chloride as a solid. Okay? The silver nitrate was aqueous, and the potassium chloride was aqueous to begin with. They're two test tubes. They're both clear. You pour them together, you get a solid product of silver chloride. Okay? Now let's look at the other one. We have potassium acetate, KCH3COO, plus silver nitrate. Okay? And they're going to form what? What are they going to make? What is it? Potassium nitrate. That's the same as earlier, right? We already know it's aqueous because potassium is aqueous with no matter what it's with. Good. And silver acetate. Okay. Now acetate is not actually on our list above. Okay. On this chart, it's not here. So I'll just tell you. This would be your solid product.
Did we assume that since silver is insoluble, that it would be?
No, because silver is not that it's insoluble, because silver nitrate is soluble. So not all silver compounds are insoluble. So we can't just make that assumption. But silver acetate would be, it's not on here, but it would be. Okay? So it's not a very good example. So we need to find the one that's soluble. Now, is it possible that you don't form a soluble product or a solid product? Is it possible you don't form a precipitate? Could both things remain aqueous? Yeah, it's possible. And then you wouldn't have a reaction occurring. It would just, your solution would remain clear. Nothing happens. Just be a clear solution. You start with the clear solution, you end up with a clear solution. Okay? So that is a possibility. Okay, now we're going to break this. Now that we know how to figure out how to find the solid or the thing that's aqueous, now we're going to learn how to break it down even further, okay, into its individual reactions that actually occur, because some of it's reacting and some of it isn't. So some of it is doing something and the rest of it's not, so we can eliminate that stuff that's not actually doing anything. And we call this the net ionic equation. So you need to learn how to write net ionic equations, because you will see those. You'll have to be able to recognize what a net ionic equation is. Okay? So the ionic equation is the thing that conveys what the ions are. What are the ions in the solution? The net ionic equation eliminates what we call the spectator ions and only leaves the reaction that is actually occurring. Okay? So that's what the net ionic. So here's an example. So here we have sodium chloride and silver nitrate. Sodium chloride, silver nitrate. It produces silver chloride and sodium nitrate. Okay, this is obviously soluble because it's sodium. It's going to be soluble. Nitrates are always soluble as well, so that's a double whammy on that one. And then we know silver or chlorine is soluble unless it's with something like silver, and then it becomes insoluble. So that's our solid product. So how are we going to write the ionic equation? The ionic equation is written by breaking everything up into its ions. Okay? So the sodium is actually sodium plus. The chlorine is actually chlorine negative. And these are all aqueous because that's what they do in water, right? They break apart. They're not together, they're broken apart in the water solution. They have broken apart. So that's how we represent them in the ionic equation. We represent them all broken apart. Now, as products, we represent the aqueous products broken apart, but the solid products we keep together because they don't break apart. They stay together, and they form a solid product. Okay, so that's the ionic equation. That's how I'd write the overall ionic equation. Now, to illustrate the next point, if we look at the product side and the reactant side, what things are the same? What's the same on both sides of the reaction? What's that? Okay, let me phrase it this way. Is sodium plus on both sides of the reaction? Yes. It's on both sides. Did it do anything? Did it react with anything? Did it change? No, it's exactly the same, right? So it didn't do anything. What about nitrate? Is it on both sides? Is it the same on both sides? Yes. It did nothing. It didn't do anything. Is there silver chloride on both sides of the reaction? No. I have a silver and a chlorine on both sides, but I don't have silver chloride on both sides. So now we can see what actually happened. What happened during this reaction? Well, silver found chlorine and formed silver chloride. That's it. That's all that happened. Everything else was eliminated because they are called spectator ions. So the spectator ions are eliminated, and you're left with your net ionic equation. The net ionic equation is written after you've eliminated all the spectator ions, the ions that did not participate in the reaction. Okay? And make sure it's balanced. All right, that's the last step. Okay, so that's how we would write a net ionic equation. Let's go ahead and write net ionic equations for these two things. Okay, so let's first write the ionic equation for potassium chloride plus silver nitrate. Okay, so I'm going to take K plus Cl minus plus Ag plus NO3 minus. Those are my ions. Those are the ones that I'm starting with. What are they going to form? What are the products of that ionic reaction? Potassium plus nitrate. They're broken apart, right? They are not together. Plus what? Silver chloride. And is it broken apart? No, it's a solid product. Solid. All these other ones are aqueous. 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 Okay, they are dissolved. The silver chloride is not. So what are the spectator ions of this equation then? What do I eliminate?
Potassium nitrate.
The potassium is the same on both sides, and the nitrate is the same on both sides. So they are eliminated, leaving me with silver silver plus Cl minus to produce AgCl. Silver chloride, this is solid, these are aqueous.
So most aqueous things would you say are going to be not included in the net ionic equation because they wouldn't be, they're more spectator ions?
Well, in this case, there's not more. There's the same number of spectator ions as there are ions that react. We have 2 spectators and we have 2 that react. So I would say it's more, usually half and half. Close to the same. Okay. All right, so now let's look at the net. What is the ionic equation for potassium acetate plus silver nitrate? Well, we have K plus CH3COO minus plus silver plus NO3 minus. That's my ionic equation. What are the products of that reaction? Well, we have K plus NO3 minus plus silver acetate. Solid. These are aqueous. Okay. What are the spectator ions? Potassium and nitrate. Those are my spectator ions. So the reaction is between silver plus acetate to form silver acetate. Solid. These are aqueous. Okay, that's my net ionic equation. Okay, and that's how I'm going to write those. Okay, now let's talk a little bit about acid-base reactions. Acid-base reactions are reactions involving transfer of H plus hydrogen ions. Okay, or in other words, what they call a proton. So if you consider the nucleus of a hydrogen atom, it has 1 proton in it. 1 single proton in that hydrogen nucleus. Surrounding that nucleus is 1 electron. If it goes from H to H plus, what's left? What is it? What happened? It lost the electron. So what's left over? A single proton. That's it. So H plus ions are protons. They're these positively charged protons that are reactive and going around and reacting with stuff. That's what they're doing. Okay? That's an acid. An acid is something that has a concentration of positively charged protons, H plus ions, greater than its base constituent, OH minus. So the H plus is greater than the OH minus, and now it's an acid. If the OH minus is greater than the H plus, it's a base. That's how you get acids and bases. Okay? So that's what the acid is, though. Acid-base chemistry happens because something donates an H plus and something accepts that H plus. So the H plus is given to something else, and that's how you do acid-base chemistry. And whenever a base accepts a hydrogen, it neutralizes it. OH plus H plus forms H2O. Water is neutral. Okay? That's acid-base chemistry. So here we have a strong acid, hydrochloric acid, and a strong base, sodium hydroxide. So really, in solution, this is H plus Cl minus plus sodium plus OH minus. Okay? The sodium and chlorine, they're not actually going to do anything. They're going to remain dissolved. They're aqueous, right? But the H plus and the OH minus are going to form H2O liquid water. So that's the reaction that occurred. So this is essentially, so this is the ionic equation. What's the net ionic equation of an acid-base reaction? H plus OH minus to produce H2O. Just like that. That's the acid-base reaction. I have a strong acid and a strong base. Okay? You form a salt, just remains dissolved, but you formed, so sodium chloride is what's left over. If you evaporated all the water, then those sodium and chlorine ions would come together. Okay? But as they are in solution, they are spectator ions. They're not doing anything. They're not reacting with anything. Okay? Okay, so that's the basis behind acid-base chemistry. Now there's another type of reaction that we have to consider, and that's oxidation-reduction. Oxidation-reduction reactions are different than transferring of protons, which is acid-base chemistry, the transfer of a proton or the acceptance of a proton. In oxidation-reduction, you're transferring electrons, or you're accepting electrons. So if you gain electrons, that's called reduction. If you lose electrons, that's called oxidation. Okay? And so we have this oxidation chemistry occurring. So here, in their example, they give you magnesium. Magnesium's in the second column of the periodic table. What kind of ion is it going to become? Well, it's going to become a magnesium 2+ ion. What does that mean? It means it lost 2 electrons. So because it lost 2 electrons, it now has a positive 2 charge on it. Well, magnesium is not going to just lose electrons because it feels like it. That's not why it loses electrons. Something causes it to lose electrons. So magnesium has to be in the presence of something that wants electrons before it will lose electrons. So that means maybe it was in the presence of chlorine. So here we have chlorine. Chlorine wants to do what? Gain or lose electrons? Gain. Chlorine wants to gain electrons. So chlorine gains electrons and it becomes Cl minus. It picks up 1 electron. Well, there's 2 chlorines there, that's why it says 2 electrons. 2 chlorines pick up 2 electrons, that's 1 electron each. Chlorine minus. We have 2 chlorine minuses. Okay? So you cannot have oxidation without reduction. If you're going to have reduction, that's because something caused you to lose electrons. Something caused you to become reduced. Okay? So that's the reducing agent, the thing that causes you to become reduced. So chlorine forced magnesium to lose those electrons because it has a greater affinity for those electrons than does magnesium. So here we have the process shown to you. Magnesium loses 2 electrons and becomes magnesium 2+. Those 2 electrons are gained by chlorine to become chlorine minus. And now you have, as your final product, these 2 charged ions. Here it was, chlorine gas in the presence of magnesium will give you magnesium and chlorine ions. They will become magnesium chloride. They will become a magnesium chloride salt. Okay? Sodium in the presence of chlorine gas would do the same thing. Sodium metal, chlorine gas together, they will form sodium chloride salt, table salt. Okay? So something is causing magnesium to lose electrons, and that is chlorine. So we need to be able to label everything. So this is, let's just say this is the reaction. Magnesium plus chlorine to form magnesium chloride. Okay? Well, I guess I will write it out as 2 plus 2 Cl minus. Okay? So this is the reaction. What lost electrons? Magnesium lost electrons. Therefore, it was reduced. What gained electrons? Chlorine gained electrons. Therefore, it was oxidized. What caused magnesium to lose electrons? What forced magnesium to lose those electrons? Chlorine. So chlorine is the reducing agent. What allowed chlorine to gain electrons? Magnesium. So it is the oxidizing agent. So, how are you going to remember all this? Well, oil rig. If you remember oil rig, you remember that oxidation is loss of electrons, and reduction is gain of electrons. If I'm oxidized, I lose electrons. Reduction is the gain of electrons. I've been doing this all backwards, haven't I? Boy, I can't even keep it straight. Reduction, oxidation. Okay, sorry, that's better. So oxidation is loss. We're losing electrons in oxidation. Reduction is the gain of electrons. Okay? And if you remember this, it will help you stay straight. Oh, they had it correct over here. Okay? So magnesium was oxidized because it lost electrons. Chlorine was reduced. Okay. So, and if you'll notice, whatever is oxidized is the agent of the other thing. It's the reducing agent. Whatever is reduced is the agent of the other thing. It's the oxidizing agent. So if you identify this, then you'll be able to identify these. And I'll tell you right now, the most common question is, what is the reducing agent? Or what is the oxidizing agent? Not whether something was oxidized or reduced. They want to know the last part. Was chlorine the oxidizing agent or the reducing agent? That's what they want to know. So you got to figure out what's oxidized or what's reduced before you can figure out the oxidizing or reducing agent. Okay? But once you do, just make sure that you're following that. Oxidation is loss of electrons. Reduction is the gain of electrons. Okay. Okay, now, one of the things that you can do through oxidation reduction is actually spontaneously create electricity. So if you have two metals and one metal has a tendency to lose electrons more than another metal in the presence of that other metal, then one of them will oxidize the other one. It will steal electrons from it. So zinc, in the presence of copper 2 plus, okay? So here, you see what zinc's doing? It is losing electrons. That means it's becoming oxidized. So zinc is becoming oxidized. Well, what caused it to become oxidized? Copper did. So that means copper is going to gain those electrons and become copper without electrons because it was copper 2 plus before. It gains those electrons. And if you pass a wire between the zinc and the copper 2 plus, it will allow electrons to actually pass through that wire. And this is what we call these voltaic cells. Okay? So one thing becomes oxidized, the other one reduced. So here's an example of what's happening. Okay? Here is a copper solution. That means the copper 2 plus ions are dissolved. This is a solid piece of zinc. You place that piece of zinc in the solution, and the copper ions will begin to trade places with the zinc atoms. The zinc atoms will come off as zinc 2 plus, and the copper ions will begin to build up around that piece of metal. They'll start to build up around it, and there will be a transfer of zinc for copper, zinc for copper, zinc for copper. And the zinc will begin to dissolve, and the copper will build up as a solid. Okay? And if you actually separate those two processes in two different containers, you can actually conduct electricity by putting a wire between them. So here is a zinc cathode, or the anode, excuse me, the zinc anode, and here's the copper cathode. So this is the copper 2 plus solution. This is a zinc piece of metal and a zinc ion solution. So we're going to pass the electrons from here to there spontaneously because these zinc ions are going to lose electrons, and as they do, they dissolve into the zinc solution. Those electrons get transferred here to the copper. The copper picks them up, and as it picks them up, it goes from copper 2 plus to copper solid, and starts to build up around that copper cathode. Okay, so it's going to build up there, and the zinc one would start to get smaller. So that's an oxidation-reduction process. That's how batteries work. So batteries are actually these processes, these metals undergoing oxidation reduction. So you want to use your cell phone? Well, you have a battery in there that is undergoing oxidation reduction processes spontaneously. It's just going through it, right? But what's going to happen eventually? Your battery's going to die, right? Why? Because maybe this whatever metal there, the zinc metal or whatever, it's run out. There's no more of it. And so it's done. It's gone. Now the process can't go anymore. Well, you can actually, through the process of electrolysis, force the electrons back. And that does what? It recharges your battery. It forces the electrons backwards, so now it's going from the copper to the zinc. Those electrons are going the other way. And then you unplug it, and they spontaneously go back again. You plug it back in, push them back the other way, and recharge your battery, right? Through this process of electrolysis, rechargeable batteries, okay? Okay, so here's some applications of oxidation reduction. Corrosion is an oxidative reductive process where iron and oxygen come together. Okay, this is iron, solid. Its oxidation state is at 0. It's not charged. Oxygen is also at 0. But when you put them together, this goes to Fe3 plus, and this goes to O2 minus. They become charged. What lost electrons? The oxygen or the iron? Iron lost 3 electrons. So was it oxidized or reduced? It was oxidized. Oxidation is loss of electrons, oil. Reduction is gain. So iron was oxidized. What was reduced? Oxygen was reduced. So what is the oxidizing agent?
No.
What's the oxidizing agent?
Oxygen.
Oxygen is the oxidizing agent, and iron is the reducing agent. Okay? Okay, this one is slightly more complicated. The idea here is that usually when you add oxygens to something, like this carbon is gaining oxygens in this reaction. That's why they call it oxidation, because you're losing electrons in that process. Okay? So with this methane molecule, you're gaining these oxygens. Okay? And they're, this would be -2, carbon +2. This is +4. These are +1, or -1, I'm sorry, -1. Okay, +1, +2. So you can see that the carbon went from a +4 state to a +2 state. Is that gaining or losing electrons? That would be gaining electrons, right? And then here, this oxygen was added to these hydrogens. Hydrogens went from a -1 to a +1 state. That's a loss of electrons. So losing those electrons, they were oxidized. And the carbon, so you have a number of things going on here with this. That's why they weren't trying to make you figure that out. And that's not something you would ever have to figure out, because that has to do with oxidation numbers, which is something you guys don't have to learn in this class. But that's essentially the idea. These are becoming oxidized, the carbons and the hydrogens, by oxygen. Okay. Bleach is an oxidizing agent. It causes things to become oxidized. And that's how they lose their color, because it oxidizes those things and they lose their color. Okay. Oops. Okay. Other processes of oxidation reduction that we see a lot in metabolism. Okay. Every time you eat sugar, the sugar goes to your blood, and then it enters your cells. That sugar in the form of glucose enters your cells as glucose 6-phosphate, which is ingenious, because then you can just draw in as much sugar as you want, because the concentration of sugar outside and inside the cell never are the same, because you changed it to glucose 6-phosphate instead of glucose. Amazing. So you bring in that sugar, and it's you're bringing as much as you want into the cell, and it undergoes glycolysis, right? It's going through glycolysis. It gets converted into a couple of ATP, but then goes through the Krebs cycle, and then you form a lot of NADH and FADH. Okay? And then those, where do those go? Those go to the electron transport chain. Okay? So in that Krebs cycle, you produce carbon dioxide, that's coming off, and then these things are going to the electron transport chain. The hydrogens of these are building up in the mitochondria, in the intermembrane space. Okay, you get all these H pluses, H plus, right? So you're building up all those hydrogens, but the electrons that were released when these hydrogens came off of this molecule, those electrons that were released, they enter the electron transport chain. And they're jumping from one cytochrome to another one, from ions, and it's like a wire. Remember this process of conducting electricity spontaneously? That's what's happening on this electron transport chain. Those electrons jump from one thing to another one because they're pulled. They're pulled along that wire, basically, because they're going to be accepted by something in the end. And that is, they're going to be accepted by these hydrogen molecules. Once they go through the ATPase pump, they're going to be accepted by those to form water with the oxygen that we breathe, right? They're going to form that water, And then through the ATP pump, you're going to produce massive amounts of ATP, which is what you need to survive. You have to have the ATP to be alive. If you didn't have it, all your processes in your body would shut down. You go through rigor mortis and you die. Okay? So, metabolism. You break down all those things that passes through. You use oxidation reduction for that. Hydrogen peroxide. We actually have to regulate the O2 minus ions in our body, the superoxide ions, because they're very reactive, and through oxidation reduction processes we have to do that. Okay. Okay. So now let's talk a little bit about balancing chemical reactions. We haven't done this, right? Or did we do balancing? No. Didn't we do a sheet on balancing?
Yes. Or no, we did story.
I didn't give you guys a sheet on balancing chemical? No? Okay. That must have been a different class. Oh, I think that was my... Oh, not that one.
Okay.
Yeah, okay. I haven't done it yet. Okay, just want to make sure. All right, so we are going to talk about how to balance chemical equations now. So we first have looked at different types of reactions. We have combination, decomposition, single replacement, double replacement, precipitation reactions, acid-base reactions, and oxidation-reduction reactions. Okay? So hopefully you would be able to identify the different types of reactions by what's going on in the chemical reaction. Is it two things coming together to form a combination reaction? Is it two metals replacing one another to form a single replacement or a double replacement reaction? Is it a process that you're losing electrons, or is it a process that you're gaining electrons? If it's H plus being transferred, that's acid-base. Okay? So now we're going to look at how do we balance any of these chemical reactions, these types of reactions that we've encountered. Okay? And balancing a chemical reaction can seem tricky at times, but once you learn the tools to use, it's not that bad. So law of conservation of mass is that all matter is neither gained or lost in the process of a chemical reaction. So it has to all be accounted for. If I start out with hydrogens and oxygens on one side, I have hydrogens and oxygens on the other side with the exact same number of hydrogen and oxygens. So there has to be an account of where everything has gone, okay, during this chemical reaction. We can't just destroy it or create it. It has to be here and here both. It's just we've rearranged those elements and created something different by rearranging them. That's all the chemical reaction has done. So here we have mercury and oxygen on one side of the reaction, okay? And we have mercury and oxygen on the other side, okay? Now we had O2 over here. So if I didn't have this coefficient of 2, then this wouldn't be a balanced chemical equation because I'm not accounting for both oxygens. So I have to put that 2 as my coefficient out front so that I have 2 oxygens. And then I have to balance the mercuries because now that I have 2 mercuries, I have to have 2 mercuries over here. And now I have accounted for all the atoms in this chemical reaction. Okay? They are the same on both sides of the reaction. Okay. Now, look at this one. Here I have how many hydrogens? Over here I have 2. Here I have 2 oxygens. Over here, 1 oxygen. Okay? So it would be so easy to balance this equation simply by doing that. H2 plus O2 produces H2O2. Okay? Why? Why is that wrong?
Changing the acidity.
Exactly. I was trying to create water. What did I create instead of water? I created hydrogen peroxide. That's not what I was making. Okay? So this is incorrect. So how am I going to maintain the identity of the H2O but still balance the oxygens? What was that? With a coefficient. I just change how many waters I have instead of changing the identity of the water, right? So instead, I can have 2 waters. That gives me 2 oxygens, right? So I put a 2 here to balance the hydrogens as well. And now I have a balanced chemical equation. 4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. This is a balanced chemical equation. Okay, I'm going to open up something here. I'm going to get to a little simulator. Okay, so let's look at this simulation. This will help us kind of understand this, okay? So here I have nitrogens, hydrogens, and they're going to produce ammonia, NH3. Well, you always have to start out with 1, of course, okay? But when you're actually writing the balanced chemical equations, if you don't have a coefficient, that represents 1. That always represents 1, okay? But if you put a coefficient of 1, then that's completely acceptable. You can do that. There's nothing wrong with that. So here I have 2 nitrogen molecules. I have 1 nitrogen molecule that has 2 nitrogens, 1 hydrogen molecule that has 2 hydrogens, and 1 ammonia molecule that has 1 nitrogen and 3 hydrogens. Okay? So, hopefully you can see this is not balanced. I have 2 nitrogens here and only 1 over here. I have 2 hydrogens and 3 over here. So, let's start with the nitrogens. Let's try to balance the nitrogens. What do I do to balance the nitrogens? I need 2 ammonias, right? I need 2 NH3s so that I can have 2 nitrogens. I have 2 nitrogens over here. I have 2 nitrogens over here. How many hydrogens do I have? 6. Okay? So this 2 gets multiplied into the H3. So 2 times 3, that's 6 hydrogens. So what am I going to do to the H2 side so that I can get 6 hydrogens? I need 3 of them. And we have a balanced chemical equation. Okay? That's a balanced chemical equation because I have the same number of everything on each side of the reaction. Okay, so here's the water equation. We did that earlier. 1 of each. Okay, so I want to balance my oxygens. So that means I need 2 waters to have 2 oxygens. And I have 4 hydrogens on this side of the reaction. So I want to have 4 on the other side. So I add another one of these, and I get a balanced chemical equation. Okay, let's try this one. Are the carbons balanced? Let's actually add 1 of each. So I have 1 carbon over here. I have 1 carbon over here. They're balanced. I have 2 oxygens here. I have 1, 2, 3 oxygens over here. I have 1, 2, 3 hydrogens here, and I have 2 hydrogens over here. 4 hydrogens over here, right? And then I have 2 hydrogens on the other side. So, let me tell you a secret. Don't try to balance the oxygens. Leave them to the end. Because you see how oxygen's all by itself right here? Because it's all by itself, if I leave it to the end, I can change it to be anything I want it to be. to make the balancing work. Okay, so leave it to the end. So what do I change to balance the hydrogens? I need 2 waters, right? And now I have 4 hydrogens. That also changed the number of oxygens. Now I have how many oxygens on the product side? 4. I have 4 oxygens on the product side, right? I have 2 oxygens on the reactant side. How do I balance it? 2. And now I have a balanced chemical equation. Okay? All right, let's try a couple of these. So we have a methane, we have a water, we have oxygen, and we have carbon dioxide, or carbon monoxide. Okay? I want to balance them. So, do I need to balance the carbons? Do I need to balance the hydrogens? Okay, now I'm going to leave hydrogens to the end. Why? Because H2 is all by itself. I can change that to be anything I need it to be. And it's not going to mess with anything. So, what else do I need to balance? Oxygens, are they balanced? Yes. Okay? Oh. So what do? I just need to balance the hydrogens. I have 4 hydrogens on the reactant side. I need 2 hydrogens on the other side. 2 hydrogen molecules have 4. Okay? Oh. What did I do?
6 hydrogens.
Oh, that's right. I have 2 more right here, huh? Yeah. Okay, so I need that. Okay, thank you. And now it's balanced. Okay? So now it's a balanced chemical equation. Let's try this one. So let's start out with 1 of each. Okay? So see, I have 2 carbons, 6 hydrogens on there. I have 2 chlorines right here. Okay? I have 2 carbons over here. 1, 2, 3, 4, 5 hydrogens. Another hydrogen here. What do I need to change? It's perfect, right? It's good. It's balanced. That happens sometimes. You'll start out and you'll be like, oh, this is already balanced. Okay? Great. So just leave it alone. Just like it is. Okay, I guess so. It's kind of a little easy. All right, so what do I need to do here? Okay, let's start with the waters. What does that do? Gives me 2 oxygens, right? So I have 2 oxygens. I have 2 carbons, 4 hydrogens. Well, when I added 2 waters here, I also added 4 hydrogens. Right? So the hydrogens are balanced. What's not balanced now? The carbons. Why did I leave that to the end? Because it's by itself. Easy, so I can change it. Okay? So with that, I'll get a balanced chemical equation. Okay? Oops. There we go. Okay, so you cannot change the subscript to balance these. So we've already done water. Yay. Water's balanced. So this is just once again showing the molecules as they are and how you would have to change the coefficient, not the subscript. You have to keep it what it is the same. Okay? So let's practice balancing these. So we have C2. Now, when you balance, this is what I recommend. Okay? You make a list. So for number 1, let's make our list. We have carbon, hydrogen, and oxygen. You have a reactant side and a product side. The number of carbons on the reactant side are 2. The number of hydrogens are 2, and the number of oxygens are 2. On the product side, I have 1 carbon, 2 hydrogens, and 3 oxygens. Okay? Is that what everybody else is getting? Are you seeing that? So this allows me to identify the things that are balanced and the things that are not balanced. So what do I need to balance? My oxygens aren't balanced. And what else? Why don't I want to balance my oxygens first? Because because they're all alone, so I want to leave them to the end because I can change them to be anything I want them to be in the end. Okay? So I balance my carbons first. That gives me 2 carbons on this side, but it changes my number of oxygens. So now instead of having 3, I have 2 times 2, which is 4, plus 1 more. 5 oxygens. So what coefficient do I need in front of oxygen O2 so that I can balance them? What times 2 is 5?
Like 1.5.
2 times 2 is 4. 2 times 3 is 6. So what's 5? 2.5. 2.5. 2.5 times 2 is 5. Now, can you actually have a half an oxygen molecule? No, you can't. This is a tool. It allows me to figure it out. Okay? I now have a balanced chemical equation, but I have to get rid of the half. So what I do is I multiply everything by 2. Because to get rid of a half, I'd multiply by 2. To get rid of a quarter, I would multiply by 4. Okay? But this is a half, so I multiply by 2. So I say I have 2 C2H2. I have 5 O2s. I have 4 carbon dioxides. And I have 2 waters. By finding the balance and then multiplying everything by 2, I maintain the balance. Okay, let's check. Oops, wrong thing. Okay, how many carbons do I have on the reactant side? 4. How many hydrogens? 4. How many oxygens? 10. Carbons on the other side? 4. Hydrogens on the product side? 4. 4 times 2 is 8, plus 2 more is 10. So I have maintained my balanced chemical equation. Okay? So I can do the half as a way to help me determine the final balance. Okay? I just can't keep it. Now, what I want you to notice about this next one is the nitrate. Do you notice how I have nitrate on one side and I have nitrate on the other side? So, keep it together. Don't break it apart. So, if I'm going to write my list, it's going to be Ag, NO3, Fe, and Cl. This is my list. Okay? How many silvers do I have on the reactant side? How many nitrates do I have on the reactant side? 1 NO3 molecule. I have 1 of them. How many Fe irons do I have? How many chlorines? 3 chlorines. Okay? All right, now let's look at the other side. On the product side, how many silvers do I have on the product side? How many NO3s do I have on the product side? 3. How many irons, Fe's, do I have on the product side? 1 iron. How many chlorines? 1. Okay, so this really helps me see what I need to do to balance this. What's not balanced? The NO3, the nitrates, and the chlorine. That's it. So let's balance the chlorines. Or the nitrates, either one of them work. Let's do the chlorines. How am I going to balance them? Say what? Put a 3 where? Okay, on the silver chloride, I put a 3. That changes my silvers to 3, and it changes my chlorines to 3. Okay? Now let's balance the nitrates. How?
Silver nitrate.
Good. So that changes my silvers to 3 and my nitrates to 3. Wow, it's a mess. And I am left with a balanced chemical equation. I have 3 silvers, I have 3 nitrates, I have 1 iron, and I have 3 chlorines on each side of the reaction. So by making this table, it just allows me to kind of keep track of everything that's going on. Okay? All right, let's try number 3. I'm going to let you guys do that one on your own. Okay, so let's make sure you guys are on track. Some of you might already have figured it out. So this is my table that I would use to do this. Okay, I have 2 carbons on the reactant side and only 1 on the product side. So I want to put a 2 in front of the carbon dioxide. That will give me 2 carbons. But that changes the number of oxygens. But let's wait. We'll figure that out in a minute because we're going to change the hydrogens also. So I have 6 hydrogens on the reactant side. I want to get 6 on the other side. So I put a 3 as my coefficient in front of the hydrogens. So that gives me 6. Okay. Now I count my number of oxygens. I have 2 times 2 is 4, plus 3 more. 4 plus 3, 7. I want to get 7 oxygens on the other side. What's my coefficient? 3.5. Yikes. Where am I? 3.5 is my coefficient. Okay, now what do I do? Multiply everything by 2 because now it's a balanced chemical equation. I have 7 oxygens on each side. So to maintain my balance but get rid of my half, I multiply everything by 2. That's going to become 2. This is going to become 7. This will become 4. And this will become 6. I have maintained my balance. I have no halves anymore. Okay? All right. So this one I'm not going to make a table for. It's pretty straightforward. Okay? So I'm going to put a 2 here, right? And how many hydrogens do I have now on the Product side,
6.
6. So I want to get 6 on the other side. Put a 3 there. And now I have a balanced chemical equation. N2 plus 3H2 produces 2NH3. And I have the same number of everything on each side of the reaction. Okay, next time, I'm going to try to remember to bring in a worksheet that we're going to try to do so you guys can practice this. Okay?